Okay, welcome everyone to today's in this seminar series. It's my pleasure to introduce today's speaker, Mr. Abhas Pradhan. He is a PhD student at the Department of Sun and Heliosphere in Max Planck Institute for Solar System Research at Göttingen. Before joining his PhD, Abhas did his integrated masters in physics at IIT Kharagpur and worked in many projects with Professor Dipankar Banerjee and Dr. Vaibhav Pant's group at IIA and then at ARIS Nainital. He is working with the Corona group under Professor Hardy Peter, and he is interested in observations of coronal heating signatures. His research work extensively utilizes solar orbiter data, which he would be describing more in this talk entitled High Resolution Observations of Active Regions Using Solar Orbiter. So with that, I would like to welcome Abhas here. The floor is yours, and Abhas has told that you can ask the questions in between his talk, but I would request that if you have very quick question, then only you ask in between, or if you have the questions that needs a long discussion, you please keep it towards the end of the talk. So with that, I would like to welcome Abhas. The floor is yours.
Thank you, Da. Uh, I think the most important part of my introduction is I started like last year. In fact, it today marks exactly 1 year into my PhD. I don't know how to feel about that, but yes, I'm extremely glad to get this opportunity to talk about what I've started working around here. A lot of these results are in a nascent stage, but yes, my work essentially is surrounding what we call as active region heating in the corona. In this talk, what I want to give is a broader picture of what the observational challenges are, how solar orbiter is going to help out address some of these. I would like, my work would be a demonstration of some of that. And what are the results are we seeing so far? Um, we are pretty optimistic about to answer some important questions regarding the corona. So, as I think most of you know about the coronal heating problem, it's a century-old problem that is about the outer atmosphere of the sun, which emits at about 1 million Kelvin temperature, and it's 100 times more hotter than the underlying photosphere. So to think about a mechanism um, that essentially explains the heating from a cooler layer and to constantly or persistently provide energy is the broader question that we were trying to answer. And on the right here, I have so-called the average profile of the solar atmosphere, where uh, if you look at heights where you have corona, there appears to be a thin layer of a few hundred kilometers called the transition layer. And this will be of importance because this, as I mentioned here, is an average profile. But if you move into regions where coronal heating rates are much higher, which is active regions where which corresponds to stronger magnetic fields, the transition region is actually pushed back. Here, when you see a temperature height plot on the left, whenever you have a higher coronal heating rate, there is conduction or energy transfer into lower layers, and you might start getting a transition layer which starts emitting in coronal temperatures as well, and you would start observing the upper transition layer in other wavelengths. So what we have is two competing heating mechanisms that have been always put forth. The first is, can we heat the corona to the temperatures 1 million Kelvin plasma to what we see using MHD waves? And MHD waves, of course, are found to be ubiquitous in the solar atmosphere. So yes, that's a good thing. We see it around all over. And they originate from lower layers and they damp or reflect in, and also they decay to other modes as well in the corona and transition layer. So they are depositing some form of energy, or they often reflect back as well. But so far, in observations that we have had so far in the studies that we have seen, is that the energy budget is too small if we look into hotter loops. And that is what I was talking about in when you were looking at active region heating, where you also have 10 million Kelvin loops up to even more than that, that start emitting X-ray temperatures. MHD waves do not fail to explain or account for that budget. So the next picture that we have, which was proposed by Parker very early on, is of nanoflares. Nanoflares has uh, soon to, like in recent, for example, literature has become an umbrella term for small scale, short-lived brightenings that originate from magnetic reconnections. Models show that we can actually use nanoflares if they are well populated and occur at at good number of frequencies. They could sufficiently heat the corona. The problem is this frequency, the distribution, the spatial and temporal distribution, all of this has not been observed well. And hence, a huge part of my study right now is what I'm trying to do here is try to understand if we can find some signatures and try to constrain these nanoflare heating models from high resolution observations. So there are three open questions that you could ask straightforward from here is how often do nanoflares occur? What are their typical energies? And um, how is the energy that one releases from a nanoflare is transported you know uh, back into the rest of the corona or into its surroundings? Is it efficient? Is it good enough with respect to the ambient surroundings? The challenge that comes here is that coronal events, when they especially happen in very small time and in very small spatial scales, are very difficult to detect. This is because the corona is very efficient in conduction, and it radiates very fast. It's very low in density as well, and so to detect a heating in action is very difficult uh, in the corona itself when things are at very small scale. However, we did see that there is this transition region which is sensitive to temperature changes, because the moment I input some amount of energy, the temperature rises by a huge amount, and also that the emission is proportional to density squared. So, and the transition region is much higher in density. So the emission itself, the signal itself is going to be much higher. So if we have a heating event up in the corona and it shows us, it deposits energy down into the transition region, we expect that the transition region counterparts of these events would show up um in a much in a more detectable fashion. It's more easy to find those. And that's where we look at what we call MOS. Uh, what is MOS? MOS is this upper transition layer emission due to heat conduction from hot coronal loops. When I say hot coronal loops, I mean more than six, let's say 3 to 5 million Kelvin loops, and which you would often see in soft X-ray images. And they are best observed in 171 passband, uh, and they're always accompanied by overlying, million Kelvin loops. So whenever you see MOS, so here's, for example, an observational um, depiction where you see in the 171 passband in SDO-AIA on the left, in the very core of active regions, you would find these mossy mottled emission, which are underlying the X-ray loops that you see on right from XRT X-ray telescope from up aboard Hinode. And yes, you would find them in active region cores. They are populated with mottled absorbing features, spicule shape light, which I will also show in movies later. it's important to note that they are in hydrostatic equilibrium with the hot loops. That means that there is a pressure balance. In fact, it has been shown in previous studies as well. You can use Moss emission um, as a diagnostic to calculate how much or estimate how much pressure the loops have. I recommend reading on the paper cited on left that describes Moss into much more detail. What is another important part is that the overall mass structure is very stable. The large scale structure is very stable for ours, and it does not suffer from projection errors. So line of sight errors um, is not a problem that we'll be dealing with, which we often deal with a lot of phenomena that happens on the solar atmosphere. Most of our estimates are in plane of sky assumptions. So this is not a case. Um, Moss is essentially an emission from a particular layer. It doesn't have a very detailed 3D structure which would be affected by uh, projections depending on line of sight. So the first observations of Moss was done by Trace, again in 171 passband. Trace had a cadence of 1 minute at best. Actually, 30 seconds at best, but it was the effective that was the instrumentation cadence, but the effective cadence actually came down to 1 minute. And this studies that came from trying to understand variability that is happening in Moss sort of hinted that the variability is around 15% less than that. Uh, and hence the that the heating that is happening in loops is most likely to be steady. Because if you start looking at, for example, what do you say, light curves from different Moss regions in different active, the variability that you would see is most likely attributed to the 5 minute oscillations, because the that you see in these mottled specular like features on Moss, and these upper layer oscillations have been directly associated with the chromospheric oscillations observed in H alpha. This is very well pointed out in this wavelet analysis that Bart does in his paper in 2003. They find that these oscillations correlate very well with what we find as H alpha um, observations. So, bearing these 5 minute oscillations, we do not see a variability in Moss with the 1 minute cadence data that we have so far. And even the hotter loops above appear to be steady in XRT. Now, XRT has a cadence of 30 seconds and it still shows around approximately 15% fluctuation level, which is similar to what the Moss variability is showing. And so they started to build a picture of that the heating in active regions is steady. There is a steady driver, or even if it's not steady, it's quasi-steady. That means the frequency is so high that it's so much higher than cooling times of the corona, which is around the order of tens of minutes. So it's not possible for us to the picture of a nanoflare starts to die out. However, when HI-C was launched as a sounding rocket mission in 2012, it had a temporal cadence of 5 seconds and an optical resolution or the spatial resolution of about zero point 0.3 to zero point 0.4 arc seconds. This is also a very generous estimate, but already we could, when we start looking at such high spatio-temporal resolution and look at Moss regions on the right, which I pointed using arrows, uh, we start seeing very short-lived brightenings of the order of less than 30 seconds. Paula Testa reports this in 2013, and these are essentially what we call as signatures of nanoflares. So heating is definitely not from steady sources anymore, because now we find these 20 to 40% increase or brightenings in the data set at many different regions are surrounding the footpoints of the hot loops. So what is happening is that there are nanoflares in corona along the loop somewhere, and they are depositing energy down into the moss regions, and they are triggering this very short-lived brightenings by a significant enhancement. Um, and these and the transport, however, could be thermal conduction, could be non-thermal electrons, and that is addressed in subsequent observations by IRIS, along which have been coupled with simulations, and they suggest that the emissions have to come from streams of non-thermal electrons. But the picture now that we see is starting to build is that they originate from nanoflare events. So so far, the evidence is suggesting that active region heating of these hot coronal loops is coming from nanoflares. The trouble, however, is that high C effectively operates for less than 3 minutes and only had one active region to see. So if something that is happening in less than 3 minutes time window at one particular in one particular active region, to generalize it for all active regions is one challenge that is always in question. The second thing is what is the frequency of these events? How often do they occur? Are these nanoflare like rapid Morse variability that we are seeing? Do they happen all throughout the lifetime of an active region? Uh, that becomes the second part of the question. The other issue was that magnetic field, which plays a huge role in generating such scenarios or such conditions. We do not have such magnetogram with similar spatial resolution that could tell us how the stresses are building, how is braid, if there's braiding happening, is there something happening at foot point, the foot point motions of these loops, how are they correlating to? And these things are some of the questions that Solar Orbiter tries to answer with its uh, extreme ultraviolet imager and its magnetogram called polarimetric helioseismic imager. So now I'm going to take a small detour into what the instrument is actually doing, so that I could explain or try to give a better picture of when I say we are observationally constrained by trying to observe, trying to detect nanoflares. So EUI has 3 telescopes. There is a full disk imager in 174 Armstrong and 304 Armstrong passbands. But what is more interesting, or more, what at least I find more interesting, is the high resolution imager at one at a Lyman alpha line and another at 174 Armstrong, and which I would refer to as HRI EUV. Now, we also have magnetograms in similar resolution as HRI, and the resolution sort of depends on where, because Solar Orbiter is in a highly elliptical orbit, the resolution depends on where you are, how far you are from the sun. So for the data set that I'm considering here, for example, from 7th March, UI and HRT, the high resolution telescope of Phi, both have a spatial resolution having a pixel scale of 180 kilometers, which is 0.5 arc second at 0.5 AU, which is effectively 0.25 arc second from Earth. And in comparison, high C was 212 kilometers pixel scale, whereas trace was 700 kilometers. So yes, we are doing much better than both. Moreover, we have 5-second cadence, which is comparable to high C. And we have 100 minutes of uninterrupted data for EUI. For the magnetogram, we have 40 minutes of data, but we only have it at 1 minute cadence. At the same time, there are some data interruptions in between. But yes, this is for an example of the high quality data that you could get. And the data that I'm considering essentially looks at this active region, the left corner here. Let's try to zoom in. Hope this movie plays. Okay. So you can already see here that this looks like moss. This looks like moss, and this is also moss. And this whole thing is an active region. The MOS emission is present in the core of it. To confirm, we have XRT data, which shows that there are very hot loops overlying both all these three possible MOS regions. And yes, we could start looking them in closer detail. And you could see that there are these specular-like motions, up and down motions, but there are also these intensity enhancements once in a while, which are very small, very localized. Uh, I would zoom even further to show you that they only last for a few frames, because if you have 5-second cadence, you have and you have like a and you're trying to look for events that are at the order of 30 seconds, something, yes, they 6 to 10 frames is what best you would see as enhancements. Let me show you in form of a light curve. And it's a clear, uh, it's a distinct feature when you start seeing them in light curves. And this is also something previously HiC had seen. And so now we start to see them in solar orbiter data as well. And so what I try to do next is I mask these regions. Um, and then I try to run uh, try a detection algorithm or method that is inspired by the previous method that Paul has just where but the problem is, since that was only a 3-minute observation window, the variability is very less. So what is happening here? Let's try to get this done. What is happening here is that you don't see the 3-minute oscillations at all. So what you could essentially do is normalize the intensity light curve to the mean of the curve, and then uh, essentially create a threshold saying anything that's above a certain amount of um, intensity threshold, I flag it as a event, and then you start to count all these nanoflare events, and you can actually see they have been flagged at above 20% or something. So versus in the bottom right corner is actually a non nanoflare or non rapid MOS variability or non high variability region that shows a lot of just background with very less variability. So similarly, what I try to do here is I run I run a moving average filter, which is of 36 frames, which is 180 seconds or 3 minutes, which is essentially one sounding rocket mission. So I run a moving average and I subtract that as my background. And whatever I find above the same threshold for 4 sigma, the sigma is calculated from this signal. I flag it as a rapid MOS variability event. And then what I do is I go back to the original light curve and I find out uh, where does it fall back to using this, where does it fall back to 2.5 sigma around the peak. And this now describes my flare-like profile, as you would say, when you, for example, look at X-ray light curves or something. Now I do this for this entire mask region, and I populate a new data set for every pixel that I get. And let's see how this looks. You start to see all these events popping in and out. Okay, so you clearly see that this is not restricted to a special time window, or it's only limited to some regions. They are present all across the MOS, and they happen. This is an entire 2-minute window video of the all total 100-minute data set, and we start to see rapid MOS variability all across the whole data set. Now, in the counterpart, where I try to look into what the magnetic field is doing, um, this is the line of sight data product from VHRT, and the real challenge here was actually to align the magnetogram data and the UI data. Data element is not trivial because the pointing information from HRT is not very accurate, and it had to be done with the help of AIA and HMI. And since the Sun Earth line it was very near to the sun-earth line essentially. So I could easily use HMI and AIA data to align my data sets. And after alignment, you can start to compare some of the features. So moss appears to come from this splash-like region, this region, and this pore-like structure. The exact inferences and discussion to be made on this is still a work in pending. It's not very easy. But yes, it does. There is some sort of variation in moss as we see they come from different regions. So it will be interesting to see if moss variability itself comes from different places or not. The takeaway that I have from my work so far is that we do observe rapid moss variability of the order of 30 seconds, which are the possible signatures of nanoflare activity. And this variability is observed all throughout the 100-minute data set. So yes, we can generalize the picture of nanoflare being a candidate for our active region heating. And the enhancement is significant, and it confirms that the high C observations of rapid moss variability over a larger or much more comprehensive data set. And when I say the enhancement is significant, it's because it is important to mention that this rapid moss variability that we observe is above the power of the 3 to 5 minute oscillations that we see. And that we know because we have applied a 3-minute filter on our data set. There is lots of further work to do. I plan to build a statistics of all these events, compare the 3 different Moss regions, how they are related to the magnetic field. There is the variability in the X-ray is also something I want to explore. I also want to mention that solar orbiter can also resolve much better. It can go as close to 0.3 AU. So we could start a pixel. We actually have observational data of 150, effectively 150 kilometer pixel scale, and 3-second temporal cadence, which is amazing. I want to mention two things here. One is that we are not addressing here about heating in quiet corona, which is also one of the things that Solar Orbiter is trying to look at using different observational campaigns, looking at the ambient quiet corona and how it's behaving. Second is it's difficult to estimate energetics without spectroscopic observations. Like every event that I'm capturing here, I do not know exactly what are the energetics of it, how much energy is being deposited, what is the actual temperature of this particular event. So that's essentially has been my work so far, and I think I have some time to talk about some earlier work that I was doing at Aries when I was at Aries, which was also related to solar orbiter. Because when we talk about nanoflares, the picture that we have is that there is a braiding of magnetic field lines, and this braiding creates stresses that are released through small nanoflare like events. But however, any form of nanoflare model that we consider, they are very reliant on how stratified these loops are, what these structures are. And the smallest substructures that we can resolve using observations will help us constrain these models as well as understand what the true structure of loops is. If you're aware of the recent debate of coronal wheel, for example, of what exactly a loop has been in question. In addition, the solar orbiter data that we have, for example, from March 17th, and if we use an enhancement, which is MGN here, we could start seeing that these substructuring to very good detail. And this is actually one of the best, most highest resolution data sets that we have of 134 kilometer per pixel. And I'll briefly go through, this is also a work in progress. I'll briefly go through what I did with Professor Deepanga Banerjee, Vaibhav Pant, and Ritesh Da. What we tried to do is put slits across some of these strands. We took 4 slices actually to improve our SNR. We try to model a background using the minima, and we try to fit Gaussians, and using full width half maxima, we try to estimate what I call widths here. For example, we find 4 different um, mm, strands that have these different widths, and we're trying to populate a new data set. And this is sort of where the picture looks at. There are 2 important observations here. One is that we see that there is a uh, depletion of population in when we go to lower resolutions, which implies that the substructuring of loops could essentially have a limit. Second is also related to self-organizing criticality, where if I'm trying to see a Gaussian/Poisson distribution, the origin of a loop is going to be very different from what we would see from a power law distribution of such loops, because of their or original random process or a binary process or something like that. So yes, this is also an interesting study which could be done from high resolution observations, and both of them sort of start building into this picture of what I would say a nanoflare model of heating. Um, and yeah, that's essentially what I wanted to talk about. Um, if you, I think there's lots more data coming up, especially uh, coordinated observations from other instruments like IRIS as well. And I hope we could build a much better picture of nanoflare models. Mm, thank you. I'd love to have questions if there are any.
Yeah, thank you, Abhas, for this great talk. And yes, now the floor is open for questions. I already see there is a question in the chat,
Mhm.
like where these data are available, how can we access? Like, could you tell something?
Okay. So if you want UI data, well, there is a solar orbiter archive which is available online where you could select from a website itself. Um, but there's also modules on Python. I think if you work in Python, you can retrieve using Fido itself. The data is all public, at least until April last year, 2023. Uh, yeah, SOAR from the SIDC Belgium group, they have their website where you can get data. That's also there.
Yeah, if you have any question, you just unmute yourself. Yeah, okay.
Yes. Hi, Abbas. Thanks for the very nice talk. So I have two questions. The first is that where you mentioned that in MHD waves usually do not contribute to heating mechanism or heating budget of
Mhm.
the corona. So that has been like a general understanding. So is that statement is still highly relevant, or like the what is the current status on those studies? Because for
Yes.
some studies I have seen, like they, for at least a small scale heating events, they in some studies they say that okay, waves can also be a possible contributor.
Yes. So yeah, I'm sort of new to this as well. And what I understand so far from discussions is and literature is that when you talk about big active regions and where you have these 10 million Kelvin X-ray loops, yes, they don't seem like a big contributor to the energy budget. However, I keep mentioning this as the quiet corona is also an unanswered and unexplored region where MHD waves could play a big role actually, because we don't see such variability when you even look at high temporal cadence data as well. Um, One, that is there. Second, it does not rule out that we shouldn't study MHD waves. MHD waves are a very good diagnostic of lot of things, especially coronal magnetic field, where it's very difficult to measure. MHD waves or coronal seismology in general becomes very important. Um, so yeah, that's
Okay,
I.
that was a general question, and another
Mhm.
very general question is that so you are studying moss in the context of coronal heating problem.
Mhm.
So how does this compare with other phenomena which are like presently talked about, like campfires and UV burst or some other events? So
Hmm.
how relevant are those in the same context?
So when I talk about Moss becomes a very only active region. Uh, uh, like Moss is essentially present where you have large, hot loops. So campfires, for example, are present in White Corona and smaller large regions as well, where you would, and that campfires become more relevant when you're trying to explain heating in quiet coronal, for example. For Moss here right now, it acts as a very good lab, I would say, where I'm trying to catch nanoflare that is happening above, and Moss starts to mm, be my place where I can start seeing signatures. So Moss is only restricted to active region signatures, whereas others can be present everywhere else. Yeah.
And what is your precise reason of calling these MOS events? I mean, their variability is there. So the only the only the only thing that you are using to call these as nanoflares is their variability right now. I mean, on what basis, like, you are uh, saying them as these are possible signatures of nanoflares?
So this
Is
isn't
it right?
exactly, yeah, I'm not very clear, but for example, this paper, there are two work by Paula herself from 2014 and 2020, where they talk about particular lines that show up because and they claim use when they compare to simulations that they show up only when there are non-thermal electrons present. And these have been observed, the iris observations have been observed in Moss regions themselves, and their time scales are also at the order of 30 to 1 minute. So any enhancement that is happening at a very small time scale is sort of correlating so far. If you compare with model simulations, they are correlating to non-thermal electrons or relativistic electrons, which can originate or which essentially originate from nanoflare reconnection.
In that
That's
study, what this study that you're showing, I think some energetics is also done where they have quantified the amount of energy in
yes,
the
they
brightening.
have done
So
that.
I thought on the basis of, I think they gave a number around 10 to the power 23 to 24 arcs.
Hmm.
So I thought on the basis of energetics, they are calling it a nanoflare. So,
Yes,
so that is why I was interested to ask that whether you are using only variability or their ubiquity, that they are occurring everywhere, and
yes,
or
no,
their
no. So that's another restriction that I have is I cannot do energetics right now if I don't have these data. But I'm
Mhm.
also using the fact that because this has been seen in high C and high C had coordinated observations with Iris, I can sort of draw one to one and say if I'm seeing variability in Moss, it's most likely to be coming from what people had seen in high C. And yeah, of course,
Okay, so
that's
I
the
guess
case.
Okay,
we can
thanks.
move towards the Kamlesh. Can you unmute yourself and ask the question?
Yeah, sure. Hello.
Hello,
So, very nice talk, Abhas, first of all. And it was very
thank you.
interesting what you are working into. Definitely the hot topic. And I have slightly, like, I have a fundamental question, not
Mhm.
maybe the observation at this point cannot answer this or cannot exactly lead us to think about it, but there are studies which says that the vertical pointing flux itself is enough, be it in quiet sun region or be it
Mhm.
in active region, both based on the observations as well as simulation. It is enough to heat, to maintain the coronal heating
Mhm.
or to transport the energy. So I was wondering when I was listening to your talk, how much contribution like comes from the pointing flux and then reconnection events, then waves. Definitely all of them. So pointing flux and waves basically carry the energy, whereas reconnection dissipates them.
Yes,
Hello,
so I think
I still there?
yeah, 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 yeah,
Yeah.
yeah, yeah.
Okay.
I
Yeah.
can, yeah. I think this is one of the very early questions that I
Yeah.
think I was thinking about, and that's why I keep I mean mentioning why fee data is important here
Mm-hmm.
is if I have good fee data for let's say a certain time window which I have we have like 40 minutes of data, we might be able to estimate some amount of from the magnetic field vector of how much pointing flux would be contributing. Yeah, I have not explored that. I cannot really comment on how much um, is it like a line of sight thing? Is magnetic field aligned incidentally showing us this emission, small like short scaled brightenings? Yeah, I
Yeah,
cannot comment
sure.
on. Mhm.
Sure, no problem in that. I was just asking this fundamental question so that we can think later and yeah,
Yes, yes, thanks
maybe
a
if
lot.
possible with anything, so we can quantify what if, because there is this different class of a class of people who believe that the pointing flux is enough, the vertical
I know, yes, I'm aware
pointing
of that.
flux, yeah, is enough to heat the any part of corona. So what amount of heating it is giving, then to separate that from the nanoflare or other class of flare energies.
Mhm.
Anyways, yeah, it was,
Thank you.
yeah,
Thank you for
okay.
that.
Okay, so then I think Aparna, can you?
Yeah, thank you, Abhas, for a very nice talk. So I was curious about the method that you're using
Mhm.
for in one of your last slides. You showed the 174 image, yeah, the previous one.
This one?
Yeah, yeah. Was how? Can you briefly explain how you're doing this?
Okay, so um, this is a very, I mean, not well known, I would say. This is essentially a MGN, multi-Gaussian normalization. So what if you have, let's say, one Gaussian filter to do unsharp masking, what this does is this allows you multiple windows to do unsharp masking, and you can define these windows. What is unsharp masking? You blur an image and you subtract that image to get sharper features. And you do that over not just one scale. So when you choose a particular Gaussian kernel, you essentially blur out a certain length scale that you are looking at. And when you subtract that, you retrieve that and remove everything else. But using multi-Gaussian normalization, you could actually retrieve multiple scales of. So if my loop strands have a range from hundreds of kilometers to thousands of kilometers, I can use multiple Gaussian kernels, and I could essentially enhance this image. This is a paper in 2015. Um, I keep forgetting. It's the Wales, the group from Wales where they have developed this. The function for this is available on Sunkit Image, which is the subsidiary of SunPy. If you're interested in using that,
What is it called?
it's called MGN, multi-Gaussian normalization.
Okay. Yeah, thank you.
Let's
Thank you so much.
use that.
Okay, we have one more question in the chat. It's like, does the nanoflares can be seen in the higher latitude near the pole? Can you explain the heating mechanism at the high latitude?
Oh, we don't see active regions a lot in higher latitudes. Well, again, an advertisement. Solar Orbiter is moving higher up the ecliptic. We would start seeing more observations to of the poles in a much high, at similar resolution. But I don't know if we could see because as I talk about, most of these observations are from active regions, and you don't find active regions in high latitudes. So yeah, not likely.
See any other questions? Okay. Then yeah, Ritesh has one. So
Okay.
Ritesh, would you like to unmute yourself or should I read it?
It's more of a comment like what Abhas was telling.
Yeah.
So as someone asked about active regions at higher latitude, it's not
Mhm.
like the active regions that we see in low latitude belts, but something very short-lived, small, uh,
Mhm.
like emerging features that we are calling as mini active regions now. Even Dipuda used to call it. But as Abhas said, like as we will be reaching more towards the polar region, the picture will become clearer.
Mhm.
But yeah, one can look in HRI data and look for those small scale, small bright active region like structures.
Mhm.
Thank you.
So I have a question, like since you are like also looking at the photospheric magnetic field with high resolution data,
Mhm.
so like the very small scale magnetic flux cancellation could also lead to this MOS variability if you.
So let's look at this. So you can see the moss on the southern side, the lower
Yeah.
end.
Mhm.
I looked into the whole 40 minutes data, and there are no parasitic polarities present
Yeah.
there.
So my question is that is it like due to limitation of our observational facilities, like we can't resolve to that certain scale, or like
I don't know. If I mean, you can always keep asking for a better instrument, but what I can say here right now is we should also start looking into how the random motions of the footpoints are affecting, because in this data set, for example, in the top right corner, there is this inclined magnetic field coming from a pore, which actually has some parasitic polarity if I scale it differently and zoom in as well. And I haven't looked if they actually undergo some sort of flux cancellation and do they affect the rates of nanoflares that I actually see on the Moss. That's an interesting idea that now comes to my mind, as you mentioned.
Yeah, I
Yep.
Nilesh want to add something or you
Mhm.
have questions?
Yeah, actually, I wanted to add, it's more like a comment that when you look at the polarities, like the one which is being displayed on the screen, so there was a paper by Pradeep Chitta and the group. The loop might be the stressed. It doesn't need to be necessarily the magnetic emergence or cancellation, but if the loop is stressed between the two polarities, between two opposite polarities through braiding, I mean, it might relax the loop, loop itself might relax, and that may lead to the nanoflare as well. So it's mix of all sort of phenomena. So that's one more thing, braiding within the staying loop, which is which relaxes to release the energy. And I think there is a paper and reference. If you are interested, I can send you that.
Okay.
Yeah.
I think
Yeah.
Abhas has also mentioned that about that braiding mechanism.
Yeah, definitely.
Yeah.
Yeah.
So one more question in the chat by Ashin. Will the moss be formed in the mini sunspot structure? What are the conditions or criteria for moss formation?
Well, one condition is that you need very hot loops. Only then the transition region starts to show this emission. In a mini sunspot, so let's see. The region that I'm looking at here itself is not one of the bigger active regions in the whole field of view. But when you want to start looking into something more smaller, for example, a bright point or something, I would expect, I don't know, we have not, I have not come across moss in smaller active regions. I don't think I can comment on that particularly. You would expect, of course, thermal conduction to start evaporating material from the lower corona. But yeah, observations have, it's also slightly difficult because you have these overarching loops from 171 itself obscuring the field of view, which they disperse more or they fan out more in bigger active regions that you can start peeking into the core of active region.
Do you have any more questions? At least I don't see in the chat. If you have any last minute quick questions, you can do. Okay, so if there is no more questions, let's thanks again to our speaker today, Abhas. It was a nice
you.
and great talk. And with that, we'd like to end the today's seminar here and see you all in the next seminar. Bye-bye.
Bye. Thank you.